Let's begin section 6.3, Sampling Distributions and Estimators. This section is not difficult, and I have a lot of vocabulary and tables, and we're going to go over them as quickly as possible. They will be posted on Brightspace as well, so that everybody gets to read it a couple of times and get the information. There is a lot, but once we get to the examples, you should be okay. So we begin with the concept of many samplings of the population in various ways to create a normal distribution of proportions and means. Characteristically, we're talking about sample proportions tend to be normally distributed and graphed as a histogram. That's once we get a sample out of the population. The mean of the sample proportions is the same as the population mean. So here we're saying that any smaller sample can be adjusted in a fashion of all the mathematical ways of getting the mean and doing them in pairs, then figuring out that they are a normally distributed item. So we're talking about sample mean. A sample mean is used to estimate a population mean if we don't have a population mean, because we know that the larger or the study of the population will come out normally distributed. Sample variances are used to estimate the population variances, and sample proportions are used to estimate population proportions. So this aspect of estimating is very critical in how we do mathematics. So we have a chart here, and the rest you can read. Put it on pause. The chart shows the proportion. It states on the sample that we have a size n. That's how many elements in our set of the data. And then we find p hat, the proportion, the percent in decimal. And then we have all of the p hats for the samples that we've taken. And then we find out that it is a normally distributed sample, no matter what. The p, lowercase p, is the population proportion, and the p hat is a sample proportion. Then we come to sample mean. The sample mean is what we'll be working on. We won't do an example on proportion. It is too lengthy as it is. The other ones are lengthy as well. But we will be doing a sample mean. A sample mean says we take a smaller section from the population of this, and then we have our X bar, the mean for that item. And then we find out that as we plot everything, we get a normal distribution. The definition by the book says a sampling distribution of a sample mean is a distribution of all possible sample means, or distribution of the variation of X bar, meaning the mean for a sample, with all samples having the same sample size n taken from the same population. The sampling distribution of the same sample mean is typically represented as a probability distribution in the format of a histogram formula and table. We're also going to be doing a variance. Notice that a variance is not normally distributed. And what we have here is the fact that a variance is skewed either to the left or to the right, depending on how large the numbers are. And it says the sampling distribution of a sample variance is a distribution of sample variances, S squared, because S is the standard deviation for a sample, with all samples having the same sample size n taken from the same population. The sampling distribution of the sample variance is typically represented as a probability distribution in the format of a table, probability histogram, or formula. And it stated that for all of them. So let's begin here. And let me Let me get that larger there. Okay, so our first example has to do with finding the mean of a sample distribution. And a genetics experiment involves a population of fruit flies consisting of 2 males named Bart and Carl and 2 females named Dana and Emily. Assume the 2 fruit flies are randomly selected with replacement. With replacement ensures randomness and independent. Very critical in doing a study that we have always an independent action, that one action that we take does not affect the next action, the independence of that. So our sample space is Bart, Carl, Dana, and Emily. So we're going to have this condition here, and we're going to take some liberties so that we can have an easier way of working it. We're going to use initials to represent Bart, Carl, Dana, and Emily. And we have 2 males and 2 females. All right, those are the things that we need to first figure out. So we're going to make our pairs. All right, to make our pairs, now remember we have Bart, Carl, Dana, and Emily. We're going to start with a B. We can have Bart and Bart because we can choose from that sample 2 elements where N is 2, and we could get both Barts. Or we can have Bart and Carl, or we can have Bart and Dana, or we can have Bart and Emily. Okay, see our pattern. Here is B, C, D, E, and all of them have B as the first gender. The first genders are male and male. The second one are also male and male. The third one is male and female. And the fourth one is male and female. Okay, so now we did the B, we're going to do the C. So we can have the CB, the CC, the CD, the CE, and the C. Oh, that's it. Sorry about that. Okay, and in this case, we have male and male, male and male, male and female, male and female. Now we're getting to the D for Dana. We can have the D and B, D and C, D and D, and in this case we have female, male, female, 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 and female. You can see that the pattern is there. And we're going to figure out how this all plays into this estimation. So our last one, of course, is Emily. Emily and Bart, D, E, and D, and E, and E. Here we have a female and a male, a female. Right. So now we want females as an average. Okay, the average of what the females are in the group. Well, there are 0 females there, 0 females there. There is 1 out of 2, right? So that's 50%, or 0.5. 0.5. Male, male is 0 female, 0. And then I have again the 50, the 50. All right, so we're getting some kind of a pattern here, but we're not comfortable with the pattern just yet because we're having the females take part. So I'm going to have female and male. I still get a half. Female and male still get a half. Female, and I get 1. Right? Female and female is 1. Female, because that's 2 females divided by 2. And that's a 1. That's that average. Then I have a half, and the 1, and the 1. All right. And I think I did that pretty well. Female, female. Yes. Okay. Let's look and see that. Okay. And so now what we're going to do is we know now we have 3 types of proportions. And I had that way up here, but I'm going to go ahead and write it here. And on proportion of females. Some of my charts don't make it easy for me. And here's probability, which is what we want for our estimation. All right, so we have 0, half, and 1. Those are the categories we have. So let's count what we have at zeros. Now we notice that we have a total of 4 times 4. We have 16 total. Now we're going to construct fractions. Because we want to make sure it equals to 1. Right. So I have 1, 2, 3, 4, 4 of them. So I have 4 out of 16 probability of, if I were to draw from here, I'd have a 0. On the halves, I have 1, 2, 3, 4, 5, 6, 7, 8. I have half coming out like that. And on the ones, I have 1, 2, 3, 4. 4 out of 16. Notice that we have a what? Yep, a normal distribution of the probabilities of these means. So, and that's what we're studying. We're proving that we have this condition happen. Very small math. So let's see what the next question says. Find the mean for the sampling distribution. Well, okay, the mean is going to be the average, right? The sum of, in this case, we're having the sum of the data divided by n, number of data. So in this case, let's look at our table here that we constructed. We have 4. We have 0 as an entry value 4 times. And then we have a half that's repeated 8 times. And we have 1 repeated 4 times. And we're going to divide all of that by the 16. All right, so this gives me half of 8 is 4 plus 4 over that 16. And we get 8/16. So our mean is a half of chances, okay, 50% chance of getting a female, at least one female from this group. Does everybody get that? All right. So we have another item here. Is the mean of the sampling distribution equal to the population proportion of females? If so, does the mean of the sampling distribution of proportions also equal the population proportion? And this time, because we're talking about percents, we're talking proportion. So the mean of the sample is at the beginning. Remember, we had Bart, Carl, Dana, and Emily. So we had a total, our N of our sample space was 4. And females had 2. So 2 out of 4 equals, you got it, 1/2, which is half, 0.5, half. Okay, from our distribution proportion, our mean, right? And we know that's our mu, our mean for our sample is equal to the mean of the data. So we have 0.5. Okay, well, they're equal. So we can clearly say, yes, the population proportion of females excuse me, of the sampling distribution of 50 is equal to the mean of the given population. And it's given because we stated at the beginning that if we do the distribution right, it will equal the trueness of it. Well, we know there's only 2 genders anyway of animals, a male or female, so it's naturally 50% of the given population. Proportion is an unbiased that's an is. Unbiased, that means it isn't affected because we have independent abilities of matching everything and coming out equally as likely. Estimator. All right. I'm going to stop right here and make this section 6.3 Part A. Okay, so because you can tell these are kind of long, but not hard. Thank you for listening.